Hello and welcome back. So this is part 4 of week 4 in advanced algorithms. As you know, in this week we have been developing the concepts of pathwidth and treewidth using tools like path decompositions and tree decompositions respectively. And the high level motivation was to see if we can extend the scope of inputs on which the kind of DP ideas that we had over trees would continue to work for problems like maximum weight independent set and possibly others. And that question led us to the development of this quantification that we now call tree width. And we hope that if a graph has bounded tree width, meaning that it has a valid tree decomposition where all the bags have size that's at most k, let's say, then we will be able to come up with DP solutions which are potentially expensive in k but polynomial in the size of the input. That's been the motivating question all along. And I'm excited for this part because we will get to see finally our first DP algorithm on graphs of bounded tree width. So we are going to continue using the maximum weight independent set problem as a running example because that's something we are already used to and it's really convenient for showcasing DP techniques. And in this part, we are just going to use the tree decomposition concept that we have recently developed. And in the next part, we are going to do this DP all over again, but using a slightly more refined notion of a tree decomposition. Now, you might ask, why aren't we just directly going on to the next part? And technically, you could actually skip this video entirely and just move on to nice tree decompositions. But I think this is still a nice warm-up and we've spent a lot of time developing definitions. So I thought this would be a nice change of scene to actually work through an algorithm instead of getting overwhelmed with even more definitions. So this is sort of place where we actually put everything that we have built up so far to some good use, and then we will see how we can do this in an even nicer way with a slightly more structured concept of a tree decomposition using the so-called nice tree decompositions. We'll get back to that next time, and that will also serve as a recap of very similar DP ideas. So in case you don't get the DP completely the first time when you watch it in this video, instead of recapping this video, you can move on to the next one, and that'll also be some sort of an automatic recap. Okay, so hopefully that sets the stage for this discussion and the next one. So let's actually begin by recalling the definition of tree width. So to that end, we said we need a tree decomposition, and a tree decomposition is a pair of objects. It's a tree and a function that associates with every node of this tree a subset of vertices of the graph G. And these subsets, we call them bags. And these are not just any collections of bags. These bags must satisfy three important properties. So you might recall that these properties are vertex coverage, edge representation, and vertex coherence. Vertex coverage simply ensures that every vertex of the graph G appears in some bag of the tree decomposition. Edge representation ensures that if you have an edge in the graph between vertices U and V, then both U and V are present together in some bag of the tree decomposition. And vertex coherence ensures that if you look at all the bags that contain a specific vertex V, then those bags collectively form a connected subtree of the tree T. So those are the three important properties that any tree decomposition must satisfy. And as we have seen, every graph has the trivial tree decomposition, which is just one bag with all the vertices thrown in. Of course, this in most cases is not an interesting tree decomposition. What we are interested in is the tree decomposition that minimizes the size of the largest bag. So that width, the width of a tree decomposition is the size of the largest bag minus 1, and the width of the tree decomposition that has the smallest width is called the tree width of the graph. So that's the concept of tree width. And before moving on to actually setting up a dynamic programming solution for the maximum weight independent set problem, I want to also be sure that we don't have a very large tree to contend with, because as you might predict, we are going to be doing the dynamic programming over the tree of the tree decomposition. not over the graph directly. So the thing is that if this tree is too big, then we are going to be spending a lot of time on the DP just navigating this tree. So we want to make sure that it's bounded in some way. So this end, we are going to introduce the concept of a non-redundant tree decomposition. Well, what does that mean? So suppose you have an edge PQ in the tree, okay? And let's say that the bag associated with P is a subset of the bag associated with Q. So XP is a subset of XQ. In this case, you might intuitively sense that XP is a redundant bag. It's just extra, we don't really need it. And if you do have that intuition, you would be absolutely right. So there is a way in which we can get rid of the bag XP and still be left with a perfectly valid tree decomposition without sacrificing the width. It's going to be a tree decomposition of the same width as the original one, so it's just as good, but it doesn't have this extra bag. So if you like, pause the video for a moment here and think about how you would modify this given tree decomposition into one where this bag XP is not there. Okay, so I hope you had a chance to think about this. So the way we are going to get rid of the bag XP is by imagining that we are folding this bag into the bag XQ, which is to say that we are deleting this vertex from the tree, and what we're doing is everything that was adjacent to XP before is now going to be adjacent to XQ instead. So that's going to be the new picture. You can try to work out a full example to be sure that this makes sense. Now, notice that in this new tree decomposition, we still satisfy all the three properties from before. The fact that you have vertex coverage and edge representation is abundantly clear because XP only had those vertices which were already present in XQ. So by deleting XP, no harm done on either of those fronts. When it comes to vertex coherence, you have to look at what happened to the structure of the tree. Notice that we did not do any major reorganization of the tree. It's almost the same as before, except that this edge basically got folded in, and everything that was seeing XP before is now going to see XQ instead. So if you focus on the subtree associated with any vertex V, if that subtree involved the vertex XP, then it must also necessarily involve the vertex XQ, because every vertex that's present in XP was also present in XQ. And because of the way our operation is designed, this subtree is still going to be a connected piece of the graph, because what happened was that in that subtree, one of the edges simply got squished. This, of course, is a very informal way of putting it. You can translate this into a formal argument, and you can develop some intuition if you're not convinced by working through an actual example, and I'll leave that as an exercise. The question I want to talk about right now is, why are we interested in performing this operation? How does it help us? So our claim is that if you have a tree decomposition which is non-redundant, which is to say that you took all of these redundant pairs XP, XQ and eliminated the smaller bags just as we discussed, then the tree decomposition that you're left with, the one that's now called non-redundant, will have at most n nodes, where n is the number of vertices in the graph G. Now, this is a nice statement to try and prove on your own, so if you like, you can pause the video here and think about why this is true. One hint is that we are going to prove this by induction. So this would be a good place to pause and give this a thought. Okay, so let's get started with the argument. I hope you had a chance to think about it yourself as well. As we hinted at earlier, we are going to prove this using induction. And here the natural thing to try and induct on would be n, which is the number of vertices in the graph G. Now the base case is reasonably clear. When n is equal to 1, the graph has just one vertex, and the trivial decomposition is just the one bag that contains that one vertex, and it's non-redundant, and it has just one node. So we are done. Now we can progress to stating the induction hypothesis and attempting the induction step. So the induction hypothesis simply states that this statement is true for all graphs with fewer than n vertices. So let's keep n fixed in our mind for the induction step. And we are going to assume that if you have a graph that has fewer than n vertices, then any non-redundant tree decomposition for such a graph will have at most as many nodes as there are vertices in the graph G. So that's going to be our induction hypothesis. Now, to actually perform the induction, we are going to start off with a leaf vertex, which is a common strategy when it comes to trees. So whenever you're performing induction over a tree-like structure, it turns out that it's often convenient to work with a leaf node. Recall that a leaf node is a node which has only one neighbor in the whole tree. Okay, so one thing that's very useful about trees is that we are always guaranteed the existence of such leaf nodes. As long as your tree has at least two vertices, you will actually find at least two nodes that have degree 1. And the reason for this is that you can pick a maximal path in the tree and you can observe that the endpoints of this maximal path, the first and the last vertex, must have degree 1. They cannot have any neighbors outside of this path because otherwise the path is not maximal, and they cannot have any neighbors on the path because that would lead to a cycle. So they must be degree 1. So that's a quick proof or justification for why we will always be able to find a leaf node to work with when we have at least two vertices, which we do because we are in the induction step. Alright, now our first observation is going to be that in this leaf, if you look into the bag that's associated with the leaf, let's say xt, it must have a vertex that only appears in that bag and nowhere else. Because if this was not true, if every vertex that appeared in this bag also appeared somewhere else, in particular by the vertex coherence property, it must also appear in the bag that is the neighbor, the unique neighbor of this leaf node. So let's say that this is our bag xt, and this t prime is the unique neighbor of t in the tree t, and xt prime is the bag associated with it. Now, if for every vertex v in xt, it is not true that it appears exclusively in the bag xt, it also appears somewhere else, then by vertex coherence in particular, it must also appear in the bag xt prime. And if this is true for every vertex in xt, then basically we see that xt is in fact redundant. We could have simply folded this bag into the neighboring bag, right? So by assumption of non-redundancy, we know that there must be at least one vertex in xt which is exclusive to the bag xt. It doesn't appear anywhere else in the whole graph. So now let's just collect all the vertices in xt which are like this, which are exclusive to the bag xt. They don't appear anywhere else. And we know that the subset is non-empty. It has at least one vertex. Now we are ready to apply the induction hypothesis. Remember that to apply the induction hypothesis, I need a smaller graph to apply it on. There's a very natural concept of a smaller graph here, for which we do have a non-redundant tree decomposition, and we should be able to prove the statement that we want to prove in one shot now. If you would like, this is a good place to again take a pause and think about it if you haven't worked out the proof for yourself already. Okay, so what is the graph that we want to pass on to the induction hypothesis? That graph is going to be G minus S. Okay, so let's remove all the vertices that appear exclusively in the bag xt. So that's the graph G minus S. And notice that if I knock out this vertex xt from the tree decomposition, so we just remove the vertex small t from the tree capital T, and therefore this bag xt is gone with it. The rest of the tree decomposition is a perfectly valid tree decomposition for the remaining graph G minus S. And well, why is that? Mainly we need to worry about vertex coverage and edge representation. So every vertex in G minus S is covered simply by definition, right? So The only vertices we removed were the vertices that only appeared in xt, so every other vertex appears in some bag other than the one that we removed. So in G minus S, every vertex is represented in this truncated tree decomposition. A similar argument accounts for edge coverage as well. So that only leaves us with vertex coherence to worry about, but notice that we have snipped out only a leaf vertex from the tree T. So any subtree that involved any vertex has only lost a leaf, so there's no way that it's going to get disconnected. So if you think about it for a minute, you will see that this tree decomposition, which is essentially T minus small t, is a valid tree decomposition for G minus S, and it's in fact non-redundant for G minus S because the original tree decomposition was non-redundant for G. So now we simply apply the induction hypothesis on this smaller tree decomposition, and we know that the tree decomposition given by T minus T must have at most n minus the size of S many vertices, because that's what the induction hypothesis tells us. So if you look at the vertex set of T minus T, its size is going to be at most the size of G minus the size of S, which is at most n minus 1, because we know that the size of S is at least 1. We removed at least one vertex. Therefore, if you put the leaf vertex back, you see that the original tree decomposition must have had only at most n nodes, which is exactly what we wanted to prove, so we are done. Therefore, without loss of generality, whenever we are given a tree decomposition for a graph G, we can assume that the tree decomposition itself has at most n nodes, where n is the number of vertices of the graph G. So this means that our dynamic programming algorithm is going to at most have to work with n of these vertices, where it's storing information and updating solutions. So now, having said all this, let's actually begin our discussion of a dynamic programming based solution to the maximum weight independent set problem. So recall that in this problem, we are given a simple undirected graph G with a weight function on the vertices, and our goal is to find a subset which is independent, that is, no pair of vertices in this subset have an edge between them, and among all such subsets, we are looking for the one which maximizes the sum of the weights of the vertices that belong to that subset. Now, given that we are discussing this in the context of tree decompositions, we are actually going to make the additional assumption that we are also explicitly given a tree decomposition of width at most k. Now, normally, you would want to just work with the problem without a tree decomposition being given to you explicitly. But right now, given a graph G, we haven't really talked about how we can compute a low width tree decomposition for it. In fact, not all graphs have tree decompositions that have small width, and you're typically interested in finding tree decompositions whose width is as small as it can be. Unfortunately, that in itself turns out to be a hard problem, and as we have hinted earlier, the best we can hope to do is some sort of an approximate solution to this question. So we can compute approximately good tree decompositions, but since we haven't discussed that yet, let's just assume that a tree decomposition is given to us as a part of the input, and that's what we have to work with. Now, given that we have this tree decomposition, our goal is going to be to solve this problem in running time that can be bounded by some polynomial function of the size of the graph, the size of the input, so something that's poly n, and we are allowed to have an overhead which is exponential in k, which is the width of the tree decomposition. Now notice that if we are able to do this, then we more or less capture the spirit of the last algorithm that we saw last week as a special case. There the input was a tree, so we know that in principle it has a tree decomposition whose width is just 1. So when we run the more general algorithm that we are going to discuss now, when the input is a tree, we just get a polynomial time algorithm just as we did before, which is very nice. Now, if your input is a tree, actually you can even compute a tree decomposition for it in polynomial time using the description that we worked out last time. So that's a completely self-contained polynomial time approach to doing maximum weight independent set on trees using the framework of tree decompositions. Of course, there we already have a very direct sort of an algorithm, and we may not necessarily appeal to this method, but it's really nice to know that whatever we are discussing now captures what we already know about trees as a special case, because our aim here was to generalize from what we know about trees. So in some sense, that's full circle and it's reassuring. Okay, so now we have our goal. We know what we are dealing with, we know what we want to find, and now we can get started on our discussion for what the DP should look like. This is also a good time to pause the video and think about whether you want to try and come up with the semantics of a DP table on your own. One hint is that it's a very natural generalization of what we were doing with trees. When we were working with trees, remember, we were standing at every node and asking ourselves, does this vertex go into our solution or does it not? Now, when you stand at a node of the tree decomposition, you have a whole bag of vertices to contend with. It's not just a single vertex. There is x sub t, which is a subset of at most w vertices from the graph G. At this point, you probably want to start thinking about all the possible ways in which a solution could interact with this subset. Now, one thing, by the way, that's useful to do is to think of the tree associated with the tree decomposition as a rooted tree. This allows you to organize the navigation of your DP table in a systematic way. Remember that when we were thinking about DP on trees, we went from the leaves all the way up to the root. So there was a natural order in which we were building up our subproblems. So here as well, let's fix an arbitrary vertex of the tree decomposition and call it the root. And let's look at some notation that's going to be useful here. So we're going to use G sub t to denote the graph induced by all the vertices which belong to the subtree that are rooted at a vertex t of the tree decomposition. Because this notation is going to be very important, let's actually illustrate this with an example. So remember, we've seen this graph before and its associated tree decomposition to the right. Now let's say that we pick this vertex in the tree decomposition as the root. Then let's look at what the tree decomposition is going to look like as a rooted tree. So I'm just going to redraw it. You can confirm by pausing the video that this is exactly the same tree decomposition as before. Notice that this happens to be a non-redundant tree decomposition. All the bags have exactly 3 vertices. There's no bag that's properly contained in another one. So that's just a nice coincidence for us. But now let's say we pick a particular vertex in this tree decomposition. So that's the highlighted vertex here, the green one, BEG. Let's say that that vertex is T. So we have highlighted the vertices BEG back in the graph. They just induce a triangle. Now if I look at T sub T, that's going to be the subtree of the tree decomposition rooted at T. And this is, of course, relative to our choice of root, which is right up here. Remember that we chose the ABC bag to be the root. So now that we have chosen T sub T as our subtree for this example, what is G sub T? Well, that's going to be the subgraph induced by the union of all the vertices that appear in the bags of this subtree T sub T. So we have BEG, EGH and BFG. If we take the union of all of those bags, we simply get BG, E and F and H. Notice that E and G in this bottom bag here are basically repeated vertices from the bag above. Similarly, B and G here are repeats as well. So the new vertices we get here are H and F, and that's the vertices right here. So now you get this sort of a structure, which is in some sense the right half of the graph that you see. So that's the subgraph G sub T. And these are going to be our subproblems actually. So if we look at these subgraphs induced by the unions of the bags of the subtrees in the tree decomposition, those are the subproblems that we are going to be building on. So now let's just go back here and ask ourselves, what are the actual things that we want to store in association with these subproblems? I'm basically asking you to think about what's the semantics of the DP table, and from here we'll try and figure out the recurrence that respects these semantics. Then we'll make sure that we actually do solve the problem if we solve these subproblems, and we are sorted on the base cases. So that's the typical DP checklist. And finally, we will analyze our DP for its running time. And that's going to be all. So take a moment here and think about how you're going to define your subproblems. Okay, so I hope you had a chance to think about that. If you remember, we said that we want our subproblems to capture all possible interactions that the optimal solution has with the bag that's associated with the tree, with the node of the tree that's currently under consideration. So let's say that we are sitting at the vertex T here, and we want to think about, well, what do we want to store at this point? Our goal is to ultimately figure out what is the maximum weight independent set of the graph GT. If we can figure that out, then we know that when we get to GR, that's the entire graph and we would be done. However, we cannot just directly hope to store the maximum weight independent set of this graph and be done with it, because as we climb up the tree, we are going to need more nuanced information about which vertices were chosen and which vertices were not chosen in our solution. Because, for example, when I guess that these vertices from my bag go into the solution, I want to have the ability to block out its neighbors, just like we did when we were solving this for grids. Except that now, instead of a previous column, I have the bags of all my children to worry about. So in general, what we are going to try and store is the following information. So for every subset of the bag, we want to store what is the best possible independent set that we can get. So that's we're going to be maximizing over the weight of the subsets here. But what properties do we want these subsets to satisfy? Well, first of all, this has to be a subset of our current universe. So this is a subset of GT. It's not a subset of the entire graph. It's a subset of the subproblem that we are currently focused on. And it's, of course, an independent subset because this is one of our local solutions, so to speak. And finally, we have to account for the constraint that comes from S. So right now, what I want is for Z to be independent and to choose precisely the subset S from my bag XT. You could also frame this the other way, where you say that I want Z to avoid S. So I want an independent set that does not pick any vertices from S. So you're welcome to try that alternate definition as well, and that works out fine too. So it's just going to be a slightly different way of modeling the recurrence. But for now, I'm going to treat S as my guess for how the independent set interacts with my bag. So you can imagine that I have a solution for this subgraph that's under consideration, and that subgraph is going to, that solution, is going to pick a certain subset of vertices from the bag XT. Now, I may not know which vertices exactly my optimal solution will pick from XT, but I can afford to try looking in an exhaustive manner at all the possibilities, because remember that we are dealing with a tree decomposition of width at most k, which means that all the bags have at most k plus 1 vertices in them. And even if I were to try all possible subsets as potentials for the choice of which vertices my optimal solution picks out from the bag, I'm still looking at only at most 2 to the k plus 1 possibilities, which is well within my goal. Remember, I'm allowed to have an exponential overhead in terms of the width. So that's what we are going to do. We are going to actually store information about all these subsets of xt, and for each subset we are going to explore the idea that if our independent set shows exactly S from the bag xt, then how large can it be? What is the maximum weight independent set that does this? And then for the final answer, of course, we can go over all these choices S and pick out the one that gave us the best solution. So hopefully it's clear that this actually leads us to the final answer, because once we are at the root, we are actually asking this question for the entire graph. And like we just said, we can go over all the values that we come up with and pick the best of them, and that will be our final answer. So we know that these subproblems make sense to compute because they do lead us to what we are looking for. Now, another thing that's easy to check off is the base cases. Now, whenever you do dp over trees, a natural place to kickstart the dp computation would be the leaves of the tree. So these are the degree 1 vertices. They don't have any children in the rooted tree. They only have one parent. Now, if T is a leaf vertex, then let's think about what we have to compute. So let's just identify a leaf vertex here, and let's say that's T. Then notice that GT is simply the graph induced by XT. There is nothing more to it because T does not have any children. Now, if we want to know what is dp of S for this leaf vertex T, notice that it only amounts to checking if S induces an independent set or not. So if S is independent itself, then, well, we know that we are going to be picking S. There's nothing else to look at. There is no subtree rooted at T. So we just record the weight of the set S itself, and that's all that there is to it. On the other hand, if the graph induced by S is not an independent set, then we know that this max is over an empty subset really, because we know that we are already going to fail to meet the condition that Z is independent, because notice that Z must contain S to begin with. In fact, Z intersection xt equals S. So we know that really the only candidate for Z is S itself. And if S is not independent, then there is nothing for us to look at. In this case, the dp value that we record is essentially undefined. One way to do that would be to store a very large negative number. So we would often denote that by minus infinity. That's the usual convention. So that's all that's going on for the base case of this dp. We are at a leaf and we are given a particular subset of the bag at the leaf, and all we have to do is check if that subset has any edges inside it. If it does, then we say this is undefined. We denote that by minus infinity if you like. And if it is an independent set, then we simply record the weight of S. So that's all that's happening at the base case. Now we can move on and think about what happens at a general node T. Now this is a good point again to take a pause and think about if you would like to give this recurrence a shot yourself. How would you compute dp of S for a particular node T in the tree decomposition, where T is an arbitrary internal node of the tree? So I'm going to put up a picture here just to guide the discussion. So we have xt, which is the bag associated with the node T, and this highlighted subset here is the subset S. And notice that the current subproblem, the world that we are living in, is G sub T. It's the subgraph that's associated with the union of all the vertices across all the bags that appear in the subtree rooted at T. But it turns out, just like when we were working with grids, when we were focused on a particular column, all that we cared about was the previous column. Similarly here, the only things that really influence our decisions are going to be the bags that are associated with the children of T in the tree decomposition. That's why I've only drawn up one layer. So by staring at this picture, you might want to think about how will you piece together information that's been pre-computed. Remember, we're working our way up from the leaves towards the root. So when we are at the computation for the node t, it's safe to assume that we have already computed the values of dp t prime of y for all subsets y of xt prime for all children t prime of t. So all of these values are at our disposal. The question is, how are we going to combine them to compute the value of dp of s at the node t? So take your time. I think it's a good idea to actually think about how would you come up with this recurrence. So come back when you've had a chance to reflect for a few minutes, and we're going to continue this discussion. All right, so let's step back for a second and think about what are we trying to do here. Remember that we are trying to compute the max weight independent set in the subgraph GT, which has the property that it picks exactly the vertices S out of the bag XT. And what we have at our disposal is similar kind of information, but about subgraphs GT prime, where T prime is a child of T. Now, what do the subgraphs GT prime and GT have to do with each other? Or if we have different subgraphs coming from the different children of T, what do they have to do with each other? So you might remember that we had discussed this useful separation property of a tree decomposition. We said that if you remove a vertex T from the tree decomposition, then the tree itself falls apart into these subtrees. And we said that if you go and look at the subgraphs corresponding to these subtrees and you remove the vertices of xt from all of them, then these subgraphs are pretty much disjoint. So the idea is that if we can just pull up the information about the maximum weight independent sets in each of these subgraphs separately, then we can more or less just add them up. And that's because the union of these independent sets would still be an independent set in the big graph, because the separation property helps us out with that. The only detail that we have to worry about is what's going on at the vertices of xt. So notice that what's going to happen is that in general, every bag, every child xt prime is going to have some vertices in common with the parent. So we are denoting with the green highlight here the vertices that are common between the parent and the child. And the shaded region within that is the vertices of S that appear in the child bag. Okay, so it may be a different subset of S that appears in each of the child bags. That really depends on the structure of the bag. It's not something that we can anticipate in advance, but this is the picture that we are working with in general. So what I want from these from the DP tables of the children of P is information about the largest possible independent set in, say, GT prime, which is consistent with the choice that we have made at the parent, the choice being that every vertex of S belongs to the independent set and every vertex that's not in S from XT does not belong to the independent set. That's the only thing that we want to force, that's the only information that we want to carry forward from parent to child, and subject to that constraint, we want to do the best that we can. So let's now zoom in to one of these children to get a better understanding of what's going on. So I've arbitrarily picked out one of the children of T, let's say that's T prime, and XT prime is the associated bag, and let's think about what kind of information we already have from the DP table that's been computed so far. So for every subset, let's say y of xt prime, we actually know the value of dp of y with respect to t prime, which is the maximum weight of an independent set, which is such that, so let's call this independent set S star for now, which is such that, well, S star of course is a subset of V of GT prime, and S star intersection xt prime is exactly equal to y. That's the kind of information that we have access to. Now, the point is that not all of these independent sets are going to be useful for me. For example, the y that I have drawn here might actually pick a vertex that I have been forbidden to pick from the constraint that I'm supposed to only choose vertices s from xt. When I say that I have to precisely pick s from xt, I know that I'm forbidden to pick anything else. So this region here is full of all of these forbidden vertices. So I'm only interested in those subsets Y which pick out exactly what they're supposed to pick out from this common region and do not touch any of the forbidden vertices. So I'm looking for subsets Y that look like this. These are the clean subsets, and as long as Y meets this criteria on this green zone, it can do anything else that it wants. So I want to go over all subsets Y of xt prime which satisfies this defining condition, this constraint that has come from above, that it can only pick, and indeed it should pick, the vertices from the orange shaded region within the green region, and it should not pick any of the vertices that are in the unshaded green region. That is the sort of Y that I am interested in. So how do we write this down in set notation? So what are we looking for? So we have the green region, which is xt intersection xt prime. And I want to say that when I look at Y in this intersection, that must match up with whatever I have from S in that intersection. So if I look at S in the green zone, these two must tally up exactly. So that's really the condition that we're looking at in set theoretic notation. But notice that we can actually simplify this a little bit further. Observe that Y is a subset of xt prime, so really Y intersection xt prime is always going to be Y. Similarly, S is a subset of xt, so S intersection xt is always going to be S. So one way of rewriting this condition that's equivalent and simpler is to say that xt intersection Y is equal to xt prime intersection S. Really, all that this means is that as far as S is concerned, we're being consistent when we pick Y. When we pick Y, we pick exactly whatever we are allowed to and that we expected to, and we don't pick anything that we are forbidden from picking. So that's what this condition is saying, except it's just saying it in set theoretic terms. So what we are going to do now is write up our recurrence, and now we know exactly what to do. We are going to say, well, we have all these dp values for all Y. We are not really interested in all Y. We will basically go over all Y that satisfy this condition that we have developed here. And among all of those, we are going to pick out the largest. Okay. Another subtlety that we have to be careful about is that we are going to be picking out these best solutions for all t prime across all the children of the vertex t. Now, because these independent sets potentially contain fragments of S, whenever vertices of S make an appearance in the child nodes, these independent sets are going to contain vertices of S. Notice that if we just took the weight of these independent sets on face value and added them all up, then the weights of some vertices of S are going to get added potentially multiple times. So what we are going to do is make sure that we subtract the weight of all the vertices that we see from S in these subgraphs to avoid overcounting these weights, and we'll simply add the weight of S one time at the end because we know that we are going to be picking all the vertices from S anyway. So let's summarize everything that we have discussed in one recurrence relation. All right, so remember we are trying to compute dp of S sitting at the node T in the tree decomposition. Just like we did for the base cases, we want to distinguish between whether S itself is locally a legitimate choice or not. So if there is an edge between two vertices of S, then we know that there's really nothing to be done. There is no extension of S that's going to be an independent set. So that's going to be an undefined entry, which we are going to denote by minus infinity. So that's an easy case out of the way. But if S itself is an independent set, then by virtue of picking S, we should add the weight of S to our solution, because we know that these are the vertices that we're surely going to be picking. That's just by definition. And now we are going to augment S using information that we have from the children of. So we are going to go over all the children, pull up the independent sets that we get from their DP tables with the adjustments that we talked about. So in particular, from the DP table sitting at T prime, we are going to go over all subsets Y which respect the constraint that comes from S. So that's written out in this compact set theoretic notation that we just developed a few minutes ago. And for all these legitimate choices of Y, we are going to pick the one that gives us the best possible answer. This is the sense in which we are being exhaustive. However, this set Y probably contains some pieces of S, and when the DP table reports the value at T prime, it's of course going to include the weight of those vertices as well, but that weight has already been accounted for when we wrote down the weight of S. So we have to make sure that we subtract the weight of all the vertices that are in both S and Y, because we want to be sure that we don't overcount it. So that's the complete recurrence, and that's your DP table. One thing that you might want to do is convince yourself of the correctness of the recurrence. Now, I'm only going to do this in high level sort of language, but if you're interested, you should look up the arguments made in section 10.4 of algorithm design by Kleinberg and Tardosh, where they write down very carefully the proof of correctness that justifies this recurrence. The way I'm going to try and reason about this is to say that this is an equality that we are trying to argue. Notice that this equality is completely straightforward when it comes to the base cases, because in the base cases, this is really an empty sum that we are looking at. There is no t prime that is a child of t, so this whole term goes away, and what we are left with is simply the weight of the set S, provided S itself is an independent. Now, it's really transparent that that's exactly what we expect this value to be at the leaves. So we are good on the base cases. At a general note, we can prove this equality in two steps. First, we can argue that the value the DP table stores is the true value of what we're supposed to get is at least what we compute it to be. And then you can separately show that it's also at most what you compute it to be. And these two inequalities together will give you the equality that you're looking for. I like to think of this inequality, the greater than or equal to, as basically saying that whatever we are claiming is in fact achievable. So the true maximum weight independent set of G sub t at least has this weight because, hey, here is a witness. Here is an independent set that actually achieves this weight. So the true max weight independent set subject to the S constraint is at least this. It's this, or maybe somebody can do better. Of course, the next inequality tells you that nobody can do better because this basically says that whatever we figured out is actually the best that you can hope for. And that's why these quantities are exactly equal. Now, to show the lower bound, to show that this is achievable, this is along predicted lines. What you would do is basically go to the DP tables of at t prime and assume their correctness by an induction hypothesis. So the correctness of this is against the backdrop of an inductive statement where you assume that the DP values at all your children have been computed correctly, and we just argued the base case a few moments ago. So according to the induction hypothesis, these values are exactly what you expect them to be. So if you get dpt prime of y is, some number, then that means that there is in fact an independent set whose weight is that claimed number in gt prime, which respects these conditions out here. Okay, so you can take these independent sets, take their union, combine it with S, and you get this overall weight. So that's the intuition for why this is achievable. The fact that when you take the union of these independent sets from different parts of the graph G, you still get an independent set. That is, there are no edges that go across. Of course, locally they are independent sets by the induction hypothesis, but the fact that when you take the union of two independent sets, in general, you may not get an independent set. There may be edges that go across, but by the separation properties of pre-decompositions, we know that it's completely safe to combine these independent sets. There are no edges going across because they come from GT prime, GT double prime. These are both separate subtrees, so you're going to have no problem. So that's something that if you're not convinced off the top of your head, it's worth checking carefully that it's safe to take the union of these independent sets. The intuition is very similar to why the DP worked when it worked for trees. When you take the union of two independent sets from two subtrees, you're not going to have any edges going across because that would give you a cycle. Here, the argument is more subtle, but you can rely on what we have argued in the previous part, where we argued the separation properties that the tree decompositions give us. This is where it plays into the argument for correctness. Now, the other side of the inequality is that you cannot do better. Here, the intuition is to argue by contradiction. You can say, well, suppose somebody does better, they give us an independent set in GT, which picks exactly S from XT, but its overall weight is bigger than what we have recorded here. Then what you can do is take this independent set and basically project it on all of these different pieces of the different children, and somewhere you're going to contradict one of the DP values for one of the children. So you're going to contradict the induction hypothesis. Now, in case this is not clear in the abstract, I'm just going to make this a little visual with some completely abstract examples. So I don't have a concrete graph to show you, but let me just draw it in a cartoonish way. So suppose we are at xt and the set S is the set that is highlighted here in blue, and let's say its weight was 10, right? And let's say this node had 3 children, and these 3 children picked out different parts of S. So xt1 has a subset of S reflected in it whose total weight is 3. xt2 has picked out a total weight of 2, and xt3 has picked out a total weight of 4 of the vertex set S. And let's say that the DP table values that we get at T1, T2, and T3 are 10, 30, and 25 respectively. So the DP table computation is going to predict a value of 10 plus 10 minus 3, 7, 30 minus 2, 28, and 25 minus 4, 21, which is a total of 66. Now suppose somebody comes along and says, no, forget this. Here is another independent set. It picks exactly the blue vertices from XT, but its total weight in GT is actually 70. We are doing better. Now, what can you do here? What you can do is say, okay, hang on, give me this subset. And let's take this independent set and basically project it on these 3 subgraphs, GT1, GT2, and GT3. By the induction hypothesis, I know that when I project this independent set on GT1, I know that from XT1, it's going to, well, exactly get a weight of 3 from the blue section of the bag, because that's all that it was allowed to pick from the green shaded region. And it's allowed to do whatever else it wants, but the maximum weight that you can squeeze out of GT1 is going to be 10 by the correctness of the induction hypothesis. So this independent set that your friend has given you that supposedly has weight 70 can have a maximum weight of 10 in GT1, because that's all that it can hope to do based on the statement of the induction hypothesis, right? And similarly, this independent set can only get a weight of 30 out of GT2. And again, it is forced to pick because of our constraint, right? So we know that this independent set was supposed to pick exactly the blue vertices from the bag XT. We know that of this 30 units of weight, which is the maximum that it can get out of GT2, two of those units must be dedicated to these blue vertices. That's just because that's what this independent set is supposed to do. If it doesn't do that, you already have a contradiction. And finally, from GT3, it's again going to be capped at a ceiling of 25. You cannot get more than 25 while respecting the condition that you must pick exactly the blue vertices from the green zone in XT3. So we know that this independent set is basically constrained in how it can behave in these three parts of the graph, and it's constrained by the induction hypothesis, right? So its total weight can really add up to at most 10, 30, and 25, but we know that it has the exact same overlaps that we have observed. So among these total weights of 10, 30, and 25, we know that we have to discount away 3, 2, and 4 because those are already being counted when we counted 10. So there's really no way that you could add up to 70 or really anything more than 66 because you're constrained by the correctness statement of the induction hypothesis. Okay. In other words, what you could also say is that to achieve a weight of 70, you must have gone beyond 10 in GT1 or beyond 30 in GT2 or beyond 25 in GT3. One of these things must have happened, but if one of those things happened, then you have contradicted the induction hypothesis. So that would not really work. So that would be the proof of correctness in the other direction, where we are saying that nobody can do better than what we have predicted in the DP tables. So therefore, the DP table computations are all correct. So there are a few pieces to these correctness arguments. Mostly they hinge on the idea that the tree decomposition has these separation properties that allow you to combine solutions as we say that we will, so that you can actually take the union, and when you calculate the value, you can take the sum of the values of the DP table with adjustments for overcounting. And the idea for saying that this is indeed the best that we can hope for, you would want to say that, well, anyone who tries to do better is going to have to face the induction hypothesis, because you can take the solution, project it, and observe what is happening in each of the individual subgraphs, and you will run into trouble over there. So that's kind of the spirit of the correctness argument. Now, the last thing that remains to be done is a running time analysis. So let's think about what we are doing here. At every node of the tree decomposition, we do have 2 raised to k values to compute, because we are computing a value for every subset of the bag X. And when we are computing these values, we are going to every child. That's why we have the summation over t prime child of t. And for each of those children, again, we are going over all subsets y which respect some additional conditions. In the worst case, we are potentially going over all possible subsets y. So we can upper bound this running time by another 2 to the k, because we know that xt prime for any t prime also has size at most k. Actually, strictly speaking, I should be saying k plus 1 and not k, because what we have been given is a tree decomposition of width at most k, which means that the bags are allowed to have up to k plus 1 vertices in them. However, as far as the running time is concerned, this is really an asymptotic estimate ultimately, so I've taken the liberty to leave out some constants. Okay, so at every node, we have, this sort of an expense here, 2 to the k times 2 to the k poly k as many times as there are children to be accounted for. So that's going to be 4 to the k poly k times d if there are d children. Now for the overall running time, remember that we're working with a non-redundant tree decomposition. So the overall running time can be estimated as an n overhead on top of this. So that's where we could leave it. But on the other hand, consider that We could also think of the overall running time in the following way. We could think of it as a sum of this quantity over all nodes in the tree of the tree decomposition. And now you pull out the 4 to the k poly k term, right? And then you're really thinking about how many tt prime pairs are there. Really, how many times does a node t prime get called in as a child of some other node? Because this is a tree, that's going to only happen once per node. So the overall running time can be bounded asymptotically by just n times 4 to the k poly k. And you could be a little more precise about the poly k if you were to carefully go and check the time that is required to do all of the sanity checks that are in place. So you could have a more careful estimate for that as well. But I'm going to leave that as an exercise and conclude this discussion here. I hope that you enjoyed this process of designing a dynamic programming algorithm for these so-called generalized trees. And it turns out that the techniques that you're learning here are actually quite widely applicable, and there are a lot of problems that turn out to be efficiently solvable on these generalized tree structures. So I hope that you will be thinking about how to solve other problems as well. You will have some opportunities through the assignments, and even more if you look at some of the reference material for this week. In the next video, we are going to be talking about nice tree decompositions, which just makes this whole process of coming up with a DP recurrence a lot more systematic. And given all the ideas that we have built up here, the discussion with the nice tree decompositions is hopefully going to feel pretty natural. So see you next time.